In this video we're going to look at two examples of objects in contact, which is where you have to draw a separate force diagram for more than one object and tie them together somehow through the algebra. They're not difficult as long as you follow the correct process each time, and in theory all of these problems are basically the same. Draw the force diagrams, set up the algebra and solve. Okay, so this first question, if you need to pause the video and read it carefully, then do. I'm going to press on and get this drawing done. So what's tempting in these cases is to draw a picture, but you should try and avoid that. Instead, try to draw a force diagram for the separate objects. So your picture might look like that, but then no, try not to do that. Try to avoid the temptation. Let's get rid of some of this and let's label the objects with their masses, and then let's start drawing some forces acting on these separate objects. So the weight is the effect of gravity on the mass of each one, which we call the weight, just going to be the mass times g. And to stop those masses accelerating towards the centre of the Earth, we need some sort of reaction, and actually in this case, if we're being proper about things, they wouldn't both be R for normal reaction, because they'd be separate, they'd be different. So maybe RT and RC for our trailer and our car. Now, as you'll see in a moment, we don't actually need the vertical forces in this case to solve this problem, so we'll ignore those in a moment. So let's look at horizontal forces. You've got the 15 kilonewton force driving the car forward, and pulling back on the car here you've got the tension in the tow rope, but of course that's the same tension that's pulling the trailer forward. So instead of drawing that line just connecting the car and trailer, do them as a separate force on each diagram. Great, let's now add the resistance forces, which is 600 on the car and 400 opposing motion on the trailer. Now I've erased the vertical forces because they could just get confusing for solving the rest of this problem, because we don't actually need those. When you do harder questions you'll need to include those probably as well. Okay, brilliant. We're all set up now to do the equations. So as a tip I would suggest starting with the object that's got the fewest forces on, in this case the trailer. And we want to link acceleration and forces, and of course F equals ma is your friend to do that. Now, before you substitute into this equation, you need to make a decision. It doesn't matter, but there are sensible options. Make a decision on what your positive direction will be. What's your positive direction? Well, the whole car and trailer thing is moving to the right, isn't it? We're all going this way, so it makes sense that positive direction should be to the right, which means T here is a positive force and the 400 resistive force is a negative force. So T minus 400 is our resultant, and that's equal to the mass 350 times A. We don't know A, so just leave it like that for now. We can't go any further than that because it's one equation with two unknowns in it. So let's now look at the car. Again, we need to choose a positive direction, but it makes sense to choose the same one as before. The resultant force this time is 15,000 minus T minus 600. And mass times acceleration this time is 750A. Now just tidying up this one here, 15,000 minus 600 is 14,400. And now there we have it, our two simplified equations. We've got two equations and two unknowns. That's simultaneous equations. So label your equations. I'm just going to rewrite them up here where I can look at them properly and solve them sensibly. Great. How are we going to solve these two equations? Well, the simplest way of doing it is to spot that in the first equation we have a positive 1t, and in the second equation we have a negative 1t. So if we add the two equations together, we'll eliminate t. Let's do that. So adding them together we get 14,400 minus 400 on the left, because these t's have all gone. On the right we have 1100a, and simply dividing by 1100 we can solve that for a. And then substituting into either of the equations to work out t, dead easy that bit, and just rounding to 3 sig fig, we get that as our answer. Okay, next question. This one is a vertical setup instead of horizontal setup. So it looks a bit different, but essentially, as I said before, the solving is very much the same. I'm just going to remove my cat who is distracting me. There we go. So we have these two masses suspended one below the other. And we're asked about the tensions in the cables holding them up or accelerating them. Let's draw some forces on then. So we've got some pulling force holding the top one up, and pulling down is going to be the tension caused by the weight, the 50 kilogram weight below, and the actual weight of the 35 kilogram mass. So you've got two forces pulling down on that. Pulling up on the 50 kilogram one, you've got the equal and opposite tension of the rope connecting the two. And of course you've got the 50 kilograms weight as well acting down here below. So there's our complete force diagram for each object. Remember, essentially you've got two separate force diagrams, even though we've drawn them in a rough configuration how they are actually arranged in real life. Right, let's start an F equals ma. On which object should we choose? Remember from before, we tend to pick the object with the fewest forces on, which is this one first. So let's do F equals ma for the 50 kilogram mass. We need to choose a positive direction. Up seems to make sense. So I'm doing positive t minus 50g. And that's going to be equal to 50 times, well, in part A, the acceleration is 0.8. We'll come to part B in a few minutes. So in this case, we don't get simultaneous equations, because in this case, we can just work out t straight away. So it's potentially a bit easier than the previous question. So that just gives us t is 530 newtons. And then let's do an F equals ma again for the 35 kilogram mass. This time we have P pulling up and these two forces here, T and 35G, pulling down. So positive P and negative for the other two equals 35 times A. And substituting for the T, it's the same T, remember it was equal and opposite here, so it's the same value of T. We can substitute this straight in here. 35G is 343 and 35 times 0.8 is 28, and that gives us P is 901 newtons. And we're done with part A. Now, if you were doing part B yourself, you would write this out separately, but for the sake of this video, I'm just going to show you how I would edit those existing equations in part B. Now, it specifically says being lowered at constant speed. Being lowered at constant speed. Does it matter whether it's being lowered or raised at constant speed? The answer is no. It doesn't matter. The important bit is here that it's at constant speed. Up or down, or not moving at all, i.e. zero constant speed, it doesn't matter. Constant speed means in equilibrium, which means the acceleration is zero. So ma is going to be zero, because a is zero. So we just basically get the resultant force is zero in both cases. And that means we're setting zero on the right-hand side of our F equals ma equations, which just gives us a new value of t. And over here, obviously that 28 is now gone, because it's now zero on the right, and we get a new value for p. And now we really are done.